Okay, so we're starting, what we're going to do in this video is we're going to talk about how to find this point using a second order approximation and a second order solution or optimization method. So first of all, if we're doing optimization, we can't like just say, okay, find the extremum, right? So I'm going to take this away because we don't really have that ability. So normally what happens is you initialize some value. So I'm just going to initialize to about 6. Normally it'd be a random number, but I'm just picking 6 because its y value is on our graph here. Oops, I didn't mean to make that. Okay. So now all I'll do is I'll just go ahead and make that point evaluated on the curve, right? So let's do the x value of e, comma, and then the function evaluated at the x value of e, right? So there's our point right there. And if I drag e around, you'll see that it goes around. Okay, so let's say we're initialized right here, all right? Now there's a couple things we can do programmatically, and one thing is compute the derivative. So what I'll just do is I'll do p prime of x. Let's see if that worked for me. That didn't work. Let's try it one more time. Let's do p prime. Okay, so this right here is the derivative of this, right? So now if I say, p prime at the x value of e, I get negative 13. So that's the slope right here, is negative 13. And then let's see if we can do p double prime, p prime prime, 6. Okay, so 6 is the second derivative, right? So I can do p prime prime at the x value of e, okay? And that's 6. Okay, so what do we have here? We have negative 13 as our slope, and 6 is our second derivative, so that's our curvature. And then the function value is 18.75, right? Okay, so now what we're going to do is we're going to use a Taylor's approximation of the function here using our derivatives, okay? So let's pop on over here. Let's make sure this is working for me. Okay, we're good to go. All right, so what we'll say f of x is going to be sort of equal to, what is our y value? It's this 18.75. So 18.75, all right? And then plus the derivative, which is negative 13. So minus 13, x minus e. What was the x value of e? It was 6. X minus 6. Right there. And then plus 1/2 of the second derivative. The second derivative is just 6 again, times 6. And then x minus 6 squared. Right, so we just want to solve this equation, right? Or, well, no, let's think about it. Okay, so this right here, this approximates our function, right? In particular, it approximates it right around here. But we know something else is it's a parabolic approximation, and this function actually is a parabola. So this thing right here is actually the exact function, which is fine. But so what we want to do is we want to solve for the x value of this. So we want to we want to take the derivative of the function, and we want to set it equal to 0. Okay, so the derivative of this function, well, this thing will go away. So f prime of x is going to be equal to, I'll just continue doing the approximately equal to, that'll go away. And so we're left with negative 13. And then what do we have here? Plus 6x. I was thinking through to make sure I did that right. Okay. Okay, so we're taking the derivative of this function and we're setting it equal to 0. So this right here is going to go away, and then here we're going to be left with negative, well, we'll say f prime of x is equal to negative 13. Okay, now the 2 comes down, plus 6, x minus 6. Okay, and now it's just, simple distribution or whatnot. Okay, so what we're going to do is we're going to set this equal to 0, right? So we're going to say 0, and we're just going to use an equal sign now. Negative 13 plus 6x minus 36. Now we're going to move this, what is that, 49 over 49 plus, 49 equals 6x. Divide the 6 and get 49 sixths is equal to x, right? So now let's look back over here. Okay, what is the what's the x value of this minimum? What did we say it was? 8.16. What is 49 divided by 6? Boom, 8.16. Okay, so the moral of the story is, if we have a parabolic approximation to a function, and in our case our function actually was parabolic, so it was perfectly right. But if we have a parabolic approximation to a function, if we can calculate the first and second derivatives, which we can, then we can find the x value of this minimum really easily with just a little bit of simple math, right? I just did Taylor series, and then I, to the second degree, and then I set it equal to 0 and solve for x, so no big deal. And actually, we may as well talk right now. So the reason that the second order approximation is nice is because, well, first of all, if we're talking about error surfaces, we know that they always are above or below 0, right? Because you can never have a negative error, right? So, we know that they're that way, and if the weights go to negative or positive infinity, then your error definitely goes to infinity. So we know that the overall error surface does look something like it's a positive up here, and then comes down and does, whatever it does, and then it comes back up here. So this parabolic approximation is not that crazy for these type of things. Of course, there's all sorts of reasons that that's wrong or right, but in general, the error surface does look up here, and then above 0 down here, and then back above 0 on this side. So this parabolic thing seems to at least have the correct end behavior, and it has the correct, it's got to be above 0 and stuff like that. So there's some nice things, and again, if we can calculate the first and second derivative at the point at which we're our first iteration or our initialization, if we can calculate first and second derivative, we can find that minimum really easily. So that's all for this one. Thanks a lot.